Okay, let's continue from where we left off. Where we left off was we saw earlier that lower the value of the burn rate pressure index, which we refer to as N, which is the N in AP raised to N, the lower it is, the lower is the sensitivity of the chamber pressure to defects in the solid propellant grain, and this is the most important consideration in developing solid rocket motors. And this conclusion leads to an important fundamental question about combustion of solid propellants. Here we will focus only on AP HTPB composite propellants, as these are the most commonly used ones. The question, the principal question is what controls the pressure index of the propellants, and the follow-up question is, can we construct a theory starting from fundamental principles of combustion to predict N? Instead of going into the details of the theory right away, I felt that the context will be, we'll have a better context to look at this question with, if you have some background on instability, which is a more serious problem when it comes to solid rocket motors. I think I'll set the stage for the discussion of the detailed discussion of the model using instability, so that the need for such a model becomes clear. Okay. Fine. So solid propellant rockets of variety of sizes are used for variety of applications. Three broad categories: very long, about 20 meters long rocket motors used as boosters in space launch vehicles, and also ballistic missiles. And the second category is tactical missiles, where the length of the rocket is a few meters long. So, okay, boosters are about 10 to 20 meters long, so are ballistic missiles like the Agni missile. But if you look at tactical missiles, they are short, they are about a few meters long. Okay. And the third class are small boosters, which are used for inertial upper stage rockets. Okay, these are the three classes. The first class is 10 to 20 meters long, the second one is about 1 to 5 meter long, the third one less than 1 meter with an L/D ratio of 1 to 2. Okay. This we have seen already. A solid rocket motor has a general structure like this, and the pressure inside the rocket as a function of time can be calculated from a simple mass balance. We derived this equation in the morning, and when you calculate the equilibrium pressure, of course you can include you can extend such an approach to get the initial ignition transient as well as the fall off after the propellant is burnt out, and you account for some transient terms. So you will get a curve like this. This is the predicted pressure time behavior of a rocket. Okay. So there is a startup, there is a steady state, and a tail off. But that is not what you get in reality. Sometimes the predicted burn rate, the predicted pressure time traces match very closely with reality. Sometimes it does not. We saw one such example yesterday, which is also repeated here, that the rocket starts off as expected, follows the expected curve, but at some point along the line the oscillations develop, and there is a DC shift in the mean, and then large amplitude oscillations around the increased mean value. Okay. Okay, let's look at it in some detail. Okay. The one important thing to note is that fluctuations always exist in systems where there is a turbulent flow. Okay. So small amplitude standing waves always exist in a chamber through which flow is happening, and rocket chambers act as a closed pipe. Okay. That is because, of course, the head end is closed with a rigid wall, and the throat is close to choked. I mean, the throat is closed, acts as a closed end because the flow is choked in that. Okay. Definition of a closed end is that the velocity at that point should not fluctuate. So at the throat, the velocity is always the speed of sound, and therefore it acts as a closed end. Okay. So in such a closed pipe, we know from the basic solution of linearized acoustic equation that standing modes, right and left travelling waves superimpose, and form standing modes, and these standing modes have very specific wavelength and frequency. Okay. The simplest way to see it is you can take a right travelling wave to be cosine kx minus omega t, take a left travelling wave to be cosine of kx plus omega t. If you add these two functions, you can show that the resulting function will satisfy the boundary conditions of closed ends only for very specific discrete values of k, okay, which is the wave number, and since the speed of the sound is fixed, that means there will be specific discrete frequencies, only specific discrete frequencies that will be allowed in allowed as standing wave solutions. Okay. So the first such standing mode will have a frequency of the sound speed divided by twice the length. Okay. I suggest that you try doing the simple case, just add cos kx minus omega t with cos kx plus omega t. You will get a function that looks like cosine kx multiplied by cosine omega t or sin kx multiplied by sin omega t, and for this combination of this product function to satisfy the boundary conditions, the k value must have a very specific form, okay, and from that you can extract the frequencies that are allowed. So the so called fundamental mode is the mode that has a wavelength that is twice the length of the chamber, okay, and a frequency that is sound speed divided by the wavelength, which is twice the length of the chamber. Okay. It will have a structure as shown here. It is a standing wave. That means that the spatial variation of it is fixed and it oscillates in a temporal way. The wave that is shown here is like this. There is pressure above the mean on the left hand side in the 0 to L by 2 and pressure below the mean from L by 2 to L, and over time this will fluctuate like this, okay, and the pressure at the center will be fixed, it will not fluctuate, okay. So in one half of the cycle, the pressure on the left hand side is above the mean, the pressure on the right hand side is below the mean. In the other half of the cycle, the pressure on the left is lower and the pressure on the right is higher, okay.
Sure. Standing wave, the node is considered as throat, right?
The node is not the throat, the node is at the center of the chamber.
Center of it.
Yeah, in this case the functional form is such that if you, the functional form that satisfies the boundary condition, the value of the pressure, okay, the value of the spatial function at L by 2 will be 0. Yeah. If I remember right, in this case this will be cos 0 at the end, cos pi at this end and cos pi by 2 at the center. Cos pi by 2 is 0. Okay. Any other questions? Yeah. So let us look at estimate frequencies for typical, the three classes of rocket motors that we saw in the previous slide. The chamber temperature is typically about 3000 kelvins, the ratio of specific heats is 1.2, R, which is the specific gas constant, is 8.314 divided by the molecular weight of the gases is about 300, it must be 287 joules per kilogram Kelvin, not kilojoules, okay, and therefore for these conditions the speed of sound will be about 1000 meters per second, okay. So A is about 1000 meters per second. So now we know the speed of sound, we can calculate what the frequencies of the fundamental modes will be for different lengths of these rockets, okay. So let us look at small boosters, length is about half a meter, therefore frequency would be about 1000 hertz, the fundamental mode. A tactical missile will have a length of about 2 meters, therefore the frequency is about 250 hertz, and for a launch vehicle booster frequency will be about 20 hertz because the length is 20 meters, okay, 20-25 hertz. So this is high frequency, intermediate frequency and low frequency. So the takeaway is that small boosters have longitudinal modes which are very high frequencies, tactical missiles have a frequency of about 250 hertz and launch vehicles have a frequency of 25 hertz, okay. So what? So this actually is at the, this becomes the most important consideration when it comes to whether these rockets can exhibit instability. What is shown here is two plots showing fluctuations in burn rate of a propellant when subjected to pressure fluctuations. Okay. Remember that there are always pressure fluctuations that exist inside a chamber, a rocket motor, and the solid propellant rocket, the solid propellant that is being used inside these rockets, the burn rate of these solid propellants depend on the static pressure that they experience, and when the static pressure inside fluctuates, the burn rate will also fluctuate. What is shown here are two cases where there is fluctuation in pressure of 1% amplitude. The blue curve is the pressure line. It has an amplitude of 0.01, that is 1% of the mean, and a frequency of 5 Hertz, a very low frequency of the kind that is found in launch vehicles. Okay. When subjected to very low frequency oscillations, you can see that the burn rate also fluctuates at about the same frequency, but the amplitude of fluctuation of the burn rate is about 0.5%. But the same propellant, when subject to 1% amplitude fluctuation at 250 Hertz, the blue line still is 1%. Okay, in both the plots, the blue line is the maximum value is 0.01, that is 1%. Here also it is 0.01, it is 1%. When the same propellant is subject to oscillations at 250 Hertz, the burn rate can fluctuate, have a fluctuation of up to 3%. Okay, this the amplitudes are the same, just the frequencies are different. This fluctuation in burn rate, a measure of this fluctuation in burn rate is what is called the response function of the propellant, which is defined as simply the percentage fluctuation in burn rate to percentage fluctuation in pressure. So for the 5 Hertz case, the response function will be half. It is about 0.005 divided by 0.01. Okay, not half, it will be it will be about half, correct, and for the 250 Hertz it will be 0.03 divided by 0.013. Okay, so the response function at 5 Hertz is half, the response function at 250 Hertz is 3. Okay, just keep this in mind. And one more thing that is not shown here is if the same calculation is done at let us say 2000 Hertz or 1000 Hertz of relevance to small boosters, you will find that the response function comes down again. So it is lower at lower frequencies, reaches a peak at about 250 Hertz and then drops back to lower values at higher frequencies. Why is this? The reason for this is the following. I will just summarize the slide. So at low frequencies, the response function is very close to the index of the propellant, which we know is a number that is less than 1, and most of the cases it is less than half. And at about 250 Hertz it has a response function of about 3, and then it drops again to at very high frequencies. This is very typical response curve, which is very similar to that of the response of a simple harmonic oscillator. So at low frequencies it just follows the forcing, then there is resonance, and then it comes back to no response case. Okay. As to what is so special about 250 Hertz, I will just explain that quickly. Okay. So you have a typical propellant piece that is burning. It has a, let us say, some complex flame structure over it, which is transferring heat flux to the surface. This is the heat flux that is coming from the gas phase. Part of this heat will go into the condensed phase, heating up the propellant from room temperature to the surface temperature, and there is some heat release that is happening at the surface of the propellant. It could be a heat release because of exothermic decomposition of certain components. It could also be heat absorption because of endothermic decomposition of some components. Okay. So the condition at the surface is generally a complex mixture of spots which undergo exothermic decomposition and other spots that undergo endothermic decomposition. Okay. If you look at the temperature profile inside the solid part of the propellant, this is the surface, let us say it is at x equals 0. If you go far away from the propellant, the temperature is room temperature, let us say 300 kelvins, and at the surface the temperature is Ts, which is usually about 800 to 900 kelvins. Okay. So, the temperature is high here and then it is low here. This usually looks like this, the profile. Okay. This is high temperature, this is low temperature. Okay. The propellant burns at a burn rate of R dot, that means the surface regresses at a rate R dot. Okay. So, the time scale for conduction is alpha divided by R dot squared. Okay. You can check that it is dimensionally correct and gives you a number which is seconds. Let me also make sure this is meter square per second, meter square, second square. So, this has dimensions of seconds. Okay. So, typical value of alpha is about 0.1 mm square per second, and typical value for R dot is 7, okay, 7 millimeters per second. Okay. So, the time scale for conduction is 0.1 divided by 7 squared, that is 50, okay, seconds. This will be equal to 20 milliseconds. I am sorry, this will be equal to 2 milliseconds. What this means is that when let us say you start under steady conditions and the surface temperature is, let us say, Ts, okay, and let us say you change Ts to Ts plus delta Ts, you suddenly change from Ts to T plus delta Ts. The typical time that it would take for the temperature profile to adjust to the new surface temperature would be about 2 milliseconds. That is what the alpha over R bar square means. Okay. It can be, this time scale can be derived more rigorously, we will see how to do that later, but right now I just want you to remember that the time scale is alpha over R bar square. Of course, it can be related to the kind of expression that we have been using between delta and alpha TR. These two can be connected, but this is usually the length and time scale relationship in diffusive phenomena governed by diffusion, but let us not worry about that. What it means is that when you change the temperature suddenly from a steady value to a new value, the typical time that it would take for this temperature profile to adjust to the new value is about 2 milliseconds. Okay. So, the frequency associated with conduction time scale, as you can see, is 1 by 2 milliseconds, which is 500 hertz. Okay. So, one of the reasons that the propellant responds to fluctuations in pressure only in the frequency range of a few hundred hertz is because the condense phase can provide the coupling which causes the fluctuation in burn rate only in that frequency range. When the changes in temperature are too slow, the response is quasi static, that means it follows the changes in the pressure, and when the pressure fluctuations are of very high frequency kind, the condense phase simply does not respond, okay, because it is being forced at a frequency that is much higher than the frequency at which it can change or the time scale that it can change. Okay. So, the reason why the frequency response of a propellant, or one of the reasons why the frequency response of the propellant is low at low frequencies, it reaches a peak at some intermediate frequencies and then drops off, is simply because the condense phase can respond to changes in or fluctuations in pressure only in the frequency range of few hundred hertz. That is associated with the time scale for conduction in the condense phase. Okay. So, launch vehicle boosters fall here, tactical missiles are in a bad spot where the propellant can actually respond very intensely to pressure fluctuations. High altitude motors do not also respond to fluctuations in pressure because the response function is small. I just want to mention one thing, emphasize one thing, the response function is defined in such a fashion that as frequency approaches 0, the response function magnitude will be equal to the burn rate pressure index of the propellant. Okay, fine, let us move on. So, it is not that there are no serious pressure fluctuations in large launch vehicle class boosters. For example, this is data from Ariane 5 of the P230 booster, okay, where it operates at 2 megapascals 20 bar, it operates fine till some point and then some oscillations are found. Okay. This is the absolute pressure, this is the differential pressure. Okay. But what I want you to notice is that there is no DC shift. Okay. In this rocket, the fluctuation is around the mean. Okay. So, when the fluctuations are around the mean and the fluctuation frequencies are also small because of the long, the motor itself being long, leads to weak coupling between acoustics and propellant combustion. We know that when forced at low frequencies, the propellant will simply passively respond to the fluctuations in pressure, and that is what is happening. The pressure fluctuations itself are maintained by vortex shed from the projecting inhibitors, okay, between different segments of the motor. The main difference between this class of instability and what is observed in tactical missiles, as you can see, is the DC shift. Okay. Here it is not just there are large amplitude oscillations, it is also that the mean itself has increased by about 25 to 40%, and then there are large amplitude fluctuations around the new mean. Okay. So, DC shift, the definition is a sudden increase in mean chamber pressure up to 30% of the design pressure. To sustain such high amplitude oscillations with a shift in mean, the energy has to come from propellant combustion. So, it is propellant combustion driven, and therefore it is strongly coupled with acoustics and propellant combustion. Yeah.
It would be useful to note that the red color stuff, the actual magnitude is just about 2%.
Yeah, correct.
Very small.
That's correct. Yeah. So, since the oscillations in the booster is driven by a fluid flow phenomena of vortex shedding and the propellant is passively responding, the energy that is there in the oscillations is very small. So, the percentage fluctuation compared to mean is very small. But if you see here, the mean is about 175 bar, the amplitude is about 25 bar. Okay. So, the amount of energy that is required to sustain such very high amplitude oscillations has to come from propellant combustion. Okay. These are the key differences between instability in space vehicle boosters and tactical rockets, and this is the key difference is these are long and these are intermediate sizes, where the frequencies are such that oscillations can be sustained by propellant combustion.